Hi and welcome to this webinar about how to set up a 3D FSI simulation in LS-DYNA. My name is Marcus and I'm working at DYNAmore Nordic, and if you have any questions please send an email to my email address here. First I will give a brief introduction about the ICFD solver, and then we will go into the model intro for the fluid and then a model intro for the structure. Then we're going to take up how to create the mesh and create the necessary keywords for the model to run. And then after we have set up the structural model, we're going to add FSI, and then we're going to run the model and look at the results. The eCFD solver is a CFD code that uses double precision, and it's an implicit solver, and it's available from version R7 of LS-DYNA, but I recommend to use the latest version R9.1. And it uses the finite element method, and it can be coupled to the structure solver, the thermal solver, the discrete element method, and the electromagnetic solver. And you can also combine several of these different solvers, so you're not limited to only couple two of them. And it has a new set of keywords, star ICFD and star mesh. And at the moment it's only a transient solver, but a steady state is under development. And if you are interested, two examples of the steady state solver is available at dynaexamples.com, but you have to contact your local distributor to get a development version of LS-DYNA. The eCFD solver has an automatic volume measure with an option to create boundary layers. So as a user, you only have to create the surface mesh, and then the solver will generate the volume mesh. But it's also possible to create your own fluid volume mesh if you want that. The fluid model that will be used is the one that I used in the previous webinar. So it's a flow over a plate. So you have a rectangular domain with a plate in the middle, and the plate will deform due to the flow. And the fluid properties is air, and with the density of 998.2 kilos per cubic meter, and the dynamic viscosity is set to 1.005 millipascal seconds. And all the measurements here in the picture is in meters, since SI units are used. And you can download the model at dynaexamples.com, and it's called Intermediate FSI Tutorial Flap. Here is a brief recap of the boundary conditions. So for the inlet, part 1, we have a prescribed velocity of 40 meters per second that is ramped up during the first second of the simulation. So it starts from 0 and then goes up to 40 meters per second. And part 2 has a 0 prescribed boundary condition, and for the part 3 we have a free slip condition, and the plate and the ground has a no slip condition. Now over to the structural model, and you can see the dimensions of the structural model here in the picture. The height is 0.5 meters, and the width is 0.4 meters, and the thickness is 0.04 meters. And the material that is used is a fictive material, since I wanted to demonstrate the deformation due to the flow in the FSI simulation. And the material model that will be used is material model 24, which is a piecewise plastic material model. And the density is set to 7,800 kilos per cubic meter, and the Young's modulus is set to 5 times 10 to the power of 10, and the Poisson's ratio is set to 0.3, and the yield stress is set to 2.3 times 10 to the power of 8, and the tangent modulus is set to 5 times 10 to the power of 8. And for the boundary conditions, so are the bottom nodes of the structure model constrained in all directions, and the rest of the nodes are free to move in all directions. Before we generate the structure mesh, it's important to make sure that the physical location or the coordinates of the structure model are the same as the fluid part 5, which is the plate in the CFD model. Otherwise the fluid structure interaction will not work. And you can use LS prepost to mesh the structure with hex elements and then save it as a keyword file or a LS-DYNA format. And it's also possible to use another preprocessor if you want, as long as it supports LS-DYNA. Or you can download the mesh from dynaexamples.com. And remember that the fluid and structure meshes do not have to have the same nodes. The only thing you have to keep in mind is that the distance d here should be smaller than 0.25 times the mean element size between the structural and the fluid model. In this model, LS prepost will be used to set up the structural model. So the first step is to include the mesh. So open up LS prepost and then locate the keyword star include in the keyword manager. And then select the mesh file that you created and save the model as solid_main.k, for example, and then reopen it to load the mesh so you can see it in LS prepost. We are first going to define the structural problem before we move on to the FSI keywords. And we will start with the material model. So in the keyword manager that you find under model and then keyword, locate the keyword map piecewise linear plasticity and enter the density, the Young's modulus and the Poisson's ratio and the yield stress and the tangent modulus, and then keep the rest of the parameters as default. And remember to press accept before you close the keyword, otherwise the changes will not be saved. And to define which element formulation we will use, this keyword section solid is used. And in this case we will use element formulation -2, which is a fully integrated solid element. And when we are creating both the section keyword and the material keyword, we can associate these two to the part keyword. So open the part keyword and enter the section ID and material ID that we just created. And here it can be important to check the subsystem. If you are in the mesh file, press setting and then change to your current input file that you are working with, and then press accept. To define the boundary conditions for the solid model, we will use boundary SPC, and we will use a node set. So under model, click on the create entity and go down to set data and set node, and then press create. And now select all the bottom nodes of the structural model and then press apply. And in the boundary SPC underscore set keyword, select the previously created node set and then constrain it in all directions, and then press accept. Now over to the control cards that we will use in the model. And since the FSI model will use a strong coupling, we have to use the implicit structure solver. And if you want more implicit guidelines, please check the implicit package out at dynasupport.com. And this package contains 2 control files that is included in the example at dynaexamples.com. But in this presentation I will only go through the necessary keywords to start the simulation and get it to work. So to trigger the implicit structure solver, use control implicit general and set the im flag here to 1 to activate it, and set the initial time step and use a high time step since we want the fluid time step to be the lowest, so the time step between the solver are controlled by the fluid. And keep the rest of the parameters as default. To control which implicit solver to use the keyword control implicit solution, and the recommended solver is the number 12, which is the new default solver from R9 for non-linear simulations. And to change it, change the nsolve parameter on the keyword, and keep the rest of the parameters as default. But one parameter that is recommended to change is the upstall value. Set it to 1 times 10 to the power of minus 20. And for more guidelines on the implicit simulations, check the implicit package that I mentioned before. And to activate the dynamics, use control implicit dynamics and set the IMAS value to 1. And for an undamped system, use the default values. And if you want to add some damping, set the gamma values to 0.55 and the beta values to 0.275630. And the last control card is the control termination, which controls the end time. Remember to set the same end time as for the fluid, and in this case we will have an end time of 1.5 seconds. Another good keyword is the control implicit auto, which activates the automatic time step for the implicit solver. And this keyword is good if you have any convergence trouble, since then the solver will try to decrease the time step. And remember to set the iAuto parameter to 1 to activate. That was all the necessary keyword for the structural part. So save the model and try to run the solid model before you add the FSI part. And that's is a good recommendation that you always try to run the structural part and the CFD part separately before you try to connect them. So now we're going to define the FSI coupling, and we don't need to change anything in the fluid model. So open LS prepost and include the structural main file, in my case solid_main.k, and the fluid_main.k, which is the main file for the CFD simulation. And then save the model as main_FSI.k, for example, and then reopen it, close LS prepost after you have saved it, and open it again to view the whole model. To add FSI to the model, we first need to define where the FSI connection will take place, and that is done with the keyword ICFD boundary FSI. So locate that keyword and select part 5, which is the plate in the fluid model, and then press insert and accept. And then we also need a control card that regulates the coupling of the FSI, and that keyword is called ICFD control FSI, and as default it uses a two-way coupling, but you can change this on the OVC parameter and keep the rest as default. You're going to run the model, use a double precision version of LS-DYNA, and I recommend to use R9.1 or a higher LS-DYNA version. And for Windows users, I recommend to use LS-Run to start your simulations, since it allows you to start both MPP and SMP calculations without using the command prompt in Windows. And for Linux, I recommend you to check the manual on how to start it, and it's often useful to use a script to start MPP simulations. So here is an example on how our command looks like when we start MPP simulations, but it will look different on each setup of Linux. But you can also use LS-Run on Linux if you want. And the model takes about 1 hour on 4 cores. To output the results, we use database binary ddplot. But since the fluid model already have this keyword, we don't need to define it again, since only one database binary ddplot is allowed per model. So if you have 2, the last one will be used, and you will see a warning in the message files. To post-process the result, open the ddplot file in LS prepost, and then hide all objects except the MS Solid, and make it transparent in the display options in the MS Post window. And then right click on MS Solid and create 2 section planes, one with the normal in the Y direction and the other with the normal in the X direction. And change the Y coordinate of the first plane to 0.34 in the object properties under that section plane. And then hold Control and click on both section planes, and right click and select group, and then select the group, and under the display options select fluid velocity in the color by field. So for state 11 it should look similar to this. So we get the fluid velocity on both section planes, and we get one legend combined for these two section planes. Then activate the solid part P solid and choose to color it by von Mises stresses. And if you look at the legend now, you will see that they are laying on top of each other. But if you left click on the legend and drag it to where you want it, you can move the legends around. And you can also change the name of the legend by changing the corresponding object in the objects window. And you change name by clicking on the object and then clicking one more time, then type in what you want to call it and press enter. And you can also create an object called vector, and if you create it on a section plane, you can control the number of vectors. So right click on the first section plane and then select vector, and then in the object properties press grid and then enter a value here for the number of points in the X direction and the number of points in the Y direction. And in this display option you can scroll down, and if you use the line mode you can only control the length of the vectors with the length scale here. But if you change to shade mode, you can control the vector size and how big the tail should be of the vector and how big the head arrows should be. For cases where you have a more complicated geometry and you have created several objects to view the results, you may want to save the post-processing, and that is available in pre-post, but for this I recommend to use the beta version of LS Prepost 4.5, since in the 4.3 version the result location is hard-coded in the saved file, but in 4.5 you can load a result from another simulation but with a similar geometry. And to save the post-processing, right click in the object window below all objects and select Save ICFD project. So below here on the white you can right click and get this menu, then click Save ICFD project, type in a name and press save in the pop-up window, and to load it you have to open LS Prepost without a dt-plot file. So just open LS Prepost and then go to the MS Post window by clicking MS and MS Post, then right click in the object window and select Load ICFD project, and then you will get a pop-up window where you select the dt-plot file that you want to be loaded. So here is how it can look if you have colored the structure with von Mises stress and colored a section plane with the fluid velocity. Then I have added streamlines that is generated from the line below the plate. And that was all that I had for this webinar. thank you for listening, and subscribe to the YouTube channel if you want to stay updated on when the next webinar will be added.